Good day, everyone. We'll consider Laplace transform in this lecture. Now, the Laplace transform is a tool used for switching between the time domain and frequency domain representation. So given a signal s of t in the time domain, should we desire to analyze the response in the frequency domain, then it will be sufficient to take the Laplace transform of the signal in the time domain s of t such that we derive s of s in the frequency domain. So therefore, the Laplace transform is used for the decomposition of a continuous time signal into the sum of the complex exponentials that are the eigenfunctions of the system. And recall that given a system, say a continuous time linear time invariant system characterized by some parameter h of x, should the input be the eigenfunction s of t, the output is seen to be the direct replica of the input, only that it becomes a scaled version of the signal, such that h of s est. So therefore, you will also recall, as was stated previously, just like as we saw, that the response of any eigenfunction can be easily determined. So meaning the output of any given eigenfunction fed into a continuous time linear time invariant system can be easily determined. And we just mentioned that the Laplace transform used for the decomposition of a continuous time signal into the sum of the complex exponentials that are eigenfunctions of the LTI system. So the implication is, now since the Laplace transform is the sum of the complex exponentials that are the eigenfunctions of an LTI system, it therefore implies that the Laplace transform can be used to evaluate the output of any type of input due to the ease of the evaluation of the eigenfunction. So hence, the Laplace transform can be used to analyze all types of signals, be it energy signal, power signal, or neither energy nor power signals. And by definition, the Laplace transform is of two types. So we have the bilateral or two-sided Laplace transform, and we have the unilateral or one-sided Laplace transform. So while the, let's change the color. Now, while the bilateral Laplace transform takes its limit of integration from negative infinity to positive infinity, the unilateral Laplace transform takes its limit of integration from 0 to positive infinity. Okay, so exactly. And why this? Now, the preference is shown for the unilateral version, especially when we desire or decide to model practical systems. Okay, practical systems. Because it is assumed that negative time does not exist. That is, t equal to negative infinity does not exist in practice. So oftentimes, practical systems are analyzed using the unilateral Laplace transform. But to develop an interesting theoretical background, the bilateral Laplace transform may be adopted in our examples. Okay. In our previous lecture, we saw that the eigenfunction of a continuous time, linear time invariant system represented by y of t are the complex exponentials, such that est is fed into a system defined by y, by lambda, and then the output y of t is given as lambda est. So in other words, y of t is the same as lambda est, which is the same as h of s est. Now, where lambda is the same as h of s, property that characterizes the system. And it should be noted that lambda is the eigenvalue. It's the eigenvalue of y of t associated with the eigenfunction. The eigenfunction, est. And s is the complex variable. So you will recall that the output, y of t, is represented by the convolution of the input s of t and the impulse response, h of t. That is, y of t is the same as s of t convolved with h of t. And this is the same as taking the limit from negative infinity to positive infinity, h of tau, s of t minus tau, d tau. Now, since the input s of t is the same as the eigenfunction, then the time-shifted signal s of t minus tau will be the same as e s t minus tau. And this is the same as est e minus s tau. Okay. And from here, we can substitute into this expression such that y of t will now be the same as taking the limits of integration h of tau e st e minus s tau d tau. And this therefore will give us, taking the limits of integration, h of tau e minus s tau d tau e st. Okay, and now if y of t is the same as negative infinity to this h of tau e minus s tau tau est, now you see that this is the same, or is of the form lambda st, which is the same as h of s est, Therefore, it follows directly that lambda, which is the eigenvalue, is the same as h of s, is the same as what we have in the square bracket. Tau s tau tau. Okay. Hence, the eigenvalue of the continuous time linear time invariant system associated with the eigenfunction is the same as h of s, which is the Laplace transform of h of t. So, therefore, this is the Laplace transform of h of t. That is, the eigenvalue is the same as the Laplace transform. Good. Now, in general, the bilateral Laplace transform, bilateral Laplace transform S of s of a continuous time sigma s of t is given as, taking the limits of integration, s of t e minus st dt. Now, where s is a complex variable, defined by s being the same as sigma plus j omega, where sigma is the damping factor and omega is the frequency in radians per second. Now, the unilateral Laplace transform, say SL of s, is given as limits of integration from 0 to infinity s of t minus st dt. So going on the plane, negative infinity to 0 to positive infinity. So it means that should we consider the entire range of time, then we say we'll be dealing with the bilateral. Now, what if we decide to consider for the duration at time t equal to 0 to positive infinity, then we'll be dealing with the unilateral Laplace transform. Good. Now, the inverse Laplace transform, which is the transformation from the frequency domain to the time domain, is given as, meaning when we decide to analyze, or better still, derive the time domain equivalent of the signal already represented or presented in the frequency domain, then we take the inverse of the Laplace transform. So first, the same as 1 over 2 pi j sigma minus j infinity to sigma j infinity s of s est dt. Now, the inverse Laplace transform shows that a signal S of t may be expressed as the sum, that is the integral, because in the time, let's say in the continuous time domain, we refer to the sum as the integral, while in the discrete domain, we use the summation. Okay, so the summation is equivalent to the integral. Okay, so just as I said, like I said earlier, that the inverse Laplace transform therefore shows that a signal S of t may be expressed as the sum of an infinite number of scaled, these are the scaled complex exponentials of the form S of x est. So the signal S of t and its Laplace transform are said to form the Laplace transform pair. That is S of t, S of x. Okay. So in other words, from S of t, we can arrive at S of s by taking the Laplace transform, and then we can arrive at S of t from S of x by taking the inverse Laplace transform. So know that it is more convenient. Now, using this formula could pose some difficulties. So it should be noted that it is more convenient to use transform pairs or partial fractions for the evaluation of the inverse Laplace transform rather than this formula. Well, we're going to play with some examples shortly. So let us consider the evaluation of the Laplace transform. Okay. I think I want to split the screen. Split the screen somewhere. Now, given the bilateral Laplace transform, S of s is the same as negative integral, negative infinity to positive infinity, S of t, e minus st, dt. Now, for all values of s being the same as sigma plus j omega, should we substitute this into this? So you see that S of s is the same as negative infinity to positive infinity, S of t, e minus into bracket sigma plus j omega t dt is the same as negative infinity to positive infinity, S of t epsilon minus sigma t epsilon j t dt. Okay. Now this is the same as taking the limits of integration. S of t epsilon sigma t j t dt. Now, soon it will become apparent that when let's change the color. Now, when epsilon minus sigma t tends to unity, that is, this tends to 0, as sigma tends to 0, then the Laplace transform will converge to the Fourier transform, such that it will now be the same as negative infinity to positive infinity s of t e minus j omega t dt. Well, that's fine. Just keep that somewhere in your mind, okay? Let's come back to what we're doing. Good. Now that we have this, the Laplace transform, for this Laplace transform to exist, for the Laplace transform to exist, now this part embraces this part. Has to be absolutely integral. This, for the Laplace transform to exist, s of t e minus sigma t must be absolutely integrable. For this expression to be absolutely integrable, then it means that the area under this curve, under this graph, must be finite. That is, negative infinity to positive infinity, the mod of s of t e minus sigma t dt must be finite. So it must assume a value that is less than infinity. And you will observe here that for this integral to be finite, we will have to determine the values of sigma for which it is finite. So what are the values? So let's put this appropriately. Now we will have to determine the values of sigma for which the integral is finite. And that brings us to the region of convergence. Okay? So in other words, since we have to figure out the values of sigma, the damping coefficient, for which the Laplace transform will be finite, then the damping factor sigma therefore gives sufficient information for the determination of the region of convergence. So the next point now is, what is the region of convergence? Okay, Now, the region of convergence is the region on the x-plane where the Laplace transform is found. Okay, so the region of convergence is the region on the x-plane for which the Laplace transform is found. So in other words, outside the region of convergence, Laplace transform will not exist. So let us consider one quick example. So let's assume S of t is the same as e minus 2 t ut. Now the Laplace transform will be integral negative infinity to positive infinity s of t e minus st dt, which should be the same as negative infinity to positive infinity e minus 2t u of t e minus st dt. Now, what's ut? Ut is a right-sided signal, right? This is a right-sided signal. So in other words, any signal to the left is truncated because it's multiplied by 0. So only signals to the right will appear. So in other words, all values of e minus 2t to the left of this graph will not appear because they are multiplied by 0. So only values of e minus 2t to the right will appear in this integration. So under that condition, we call that this extends to negative infinity. So it means all values from negative infinity to 0 will not appear. So technically, the u of t will alter the limit of integration such that the negative infinity will disappear because all values from negative infinity to 0 will become 0, and the integral of 0 is 0. So we can now rewrite that this is now from 0 to infinity because all values from negative infinity to 0 is now 0. Then e minus 2t e minus st dt. Now the u of t has performed that operation by changing the limits of integration, so it doesn't have to appear again. So we now have this. Good. Then this therefore becomes 0 to infinity epsilon, that is s plus 2 minus s plus 2 t dt. This will be the same as 1 minus 1 over s plus 2 into brackets e minus s plus 2 t, taking our limits from 0 to infinity. So this will now give us minus 1 over s plus 2 into brackets epsilon, and infinity multiplied by this will be epsilon infinity minus epsilon 0. So this will reduce to 0, and this is equal to 1. So what we have is minus 1 over s plus 2 times minus 1 equal to 1 over s plus 2. Now, the Laplace transform in this case is 1 over s plus 2. Now, recall that we already established that this signal is right-sided. because all the components are appearing to the right, since the signal is multiplied by the unit step function, not the scaled version of it. So if u of t was scaled such that it is u of minus t, then values from negative infinity to 0 will appear, while from 0 to positive infinity will disappear, be multiplied by 0. Good. But the point here is we want to figure out if this Laplace transform truly exists. Does it have a finite value? Now we have to figure out the region of convergence. And we already established that the region of convergence is the region on the x-plane for which the Laplace transform is finite. And recall in our previous lecture that the x-plane looks something like this: j omega on the y-axis and sigma on the x-axis. So in other words, we'll have to plot some parameters here, okay? And the parameters we have to plot here are sigma, because we said we already established that this sigma is an interesting parameter that helps us figure out the region of convergence. So in other words, our plot will definitely be parallel to the y-axis. Okay? So should we be able to determine the damping factor, then we should be able to tell if the signal will have a Laplace transform. Good. Now we have the Laplace transform. Yeah, well, not trying to jump the gun, but we'll talk about it much later. Now, when we have, should I go into that now? I should just mention, because we'll have to talk about zeros and poles, okay? And, okay, let's take it in bits and pieces. I'll come to that shortly, okay? But when the Laplace transform is a rational fraction, then the roots of the numerator are referred to as the zeros, while the roots of the denominator are referred to as poles. Okay? Okay, so the roots of the numerator, this is the numerator. They are the zeros, while the roots of the denominator are the 0. And how do we figure this out? Well, we equate whatsoever we have, either the numerator or denominator, to 0. Okay? And the roots are plotted on the x-plane. This is the x-plane. On the x-plane. Okay? So once we plot those values on the x-plane, then we'll be able to tell. Now, in this case, we have roots, we have poles. We have a pole here, okay? Because should we equate the denominator to 0, that is s plus 2 equal to 0, then s is the same as minus 2. So that is a pole. So a pole is a value that forces the denominator to 0. The denominator to 0. Okay? So because when s is minus 2 plus 2 is equal to 0. So that is a pole. Okay? Why And if a pole forces the denominator to 0, then it means that a pole forces the Laplace transform to infinity, right? Yeah, because anything over 0 is infinity. But that's not where we are going to right now. Okay? So let's not get everything all along. So let's take this one step at a time. Now that we have been able to figure out the pole, then we plot it on the S-plane. Okay? So here's the X-plane. This is J omega. This is sigma. And S is -2. So this is 0. This is negative positive. So -2 will be somewhere here, right? -2. -2. Okay. Now, recall that I already mentioned that the sigma is multiplied by u of t. So by the direction of u of t, we know that it is a right-sided signal. And for a right-sided signal, it means that the region of convergence will be to the right. For a left-sided signal, the region of convergence will be to the left. We're going to talk about the properties of the region of convergence. But one thing to note is that the region of convergence must not include any pole, okay? Now, region of convergence must not include any pole. And now we have a pole at x -2. So if we should, now the plot will be parallel to the j omega axis. So that's the plot, okay? Completed the plot. But what part is the region of convergence? We already understand it must not include a pole. So if we should trace a region of convergence to the left, then it's going to include a pole. So the only part that excludes a pole here is to the right. And recall, it is a right-sided signal, okay? So usually, the region of convergence is in the direction of the signal, okay? So this is the region of convergence. Now, observe that the region of convergence includes the j omega axis, okay? So that's one important point to also note, okay? So when the region of convergence includes the j omega axis, we say the system is stable, okay? So that's stability, system stability, okay? So when the region of convergence includes the j omega axis, the system is said to be stable. Otherwise, it is unstable. So now that we have been able to figure this out, so we can tell that the Laplace transform will exist in the region of convergence. So outside this region, the Laplace transform will not exist. So in other words, Laplace transform will not exist in this region, okay? But it will exist in the region. Okay, so let's consider a few properties of the region of convergence. Split screen. So the first point to note here is that the region of convergence never contains any pole, just like I mentioned. And then the second point is the region of convergence is always the region of the x-plane to the left or right of the vertical line, or a strip between two vertical lines. So let's put that down. ROC. Or a strip between two vertical. Now, let us say this is j omega, this is sigma. So we said to the left, forget it's a vertical line. So it's either to the left. It could also look something like this. Let's say it's either to the right. Then it could also look something like this. J omega, it could be a strip. This is another type of strip. Okay? Strip between two vertical lines. Then the third point is that if S of t is right-sided, then the region of convergence is right-sided. Just like I mentioned earlier. So let's assume the signal is right-sided. Then the region of convergence, j omega sigma, is going to be right-sided. Okay? And if the signal S of t is left-sided, then ROC is left-sided. So let's assume the signal is left-sided, then j omega sigma should be left-sided. ROC will be left-sided. These are the region of convergence, okay? ROC, ROC, C. Okay. Region of convergence. Okay. So the next point to notice, if S of t is two-sided, or better still, it is the sum of the left and right-sided signal, the ROC is either a strip or else the individual ROCs will not overlap. And when they don't overlap, thereby produces a null. means when there is no overlap, then there is no Laplace transform. So what's the implication? So this gives us something like a strip, right? J omega sigma. So when we have probably this signal is right-sided, this is left-sided, so this is the region of convergence, right? So there is an overlap. Now, the second case here is because here we have the sum two-sided signals or the sum of the left and the right-sided signal, which is this. Then, alternatively, the ROC is either a strip or else the individual ROCs may not have overlap. So let's assume we have something like this, and we have something like this, and this happens. Say this is ROC1, this is ROC2. So there is no overlap. So in this case, no overlap. So no Laplace transform. Okay. Okay, and then the next property here is if S of t is finite duration, then the region of convergence is the entire S-plane. So let's assume we have a signal of finite duration. Okay, so this is 1 of t. So let's say this is 0, this is k. Okay, so what we are saying here is that the region of convergence is the entire x-plane with some exception. So we have value negative infinity at 0 and positive infinity. So at these values, excluding those values, every other part is the region of convergence. Okay. So the region of convergence excludes negative infinity, 0, positive infinity. Okay. Though I already mentioned the poles and zeros, let's just designate it properly. Poles and zeros, Laplace transform. So if S of S, but that's still S of S will always be a rational fraction for S such that S of S is the same as A0, S of M, plus A1, S of M minus 1, plus A2, S of M minus 2, plus all the way to plus AM divided by B0, S of N, B1, S of N minus 1, plus B2, S of N minus 2, plus the way plus Bn. And this is the same as A0, S minus Z1, S minus Z2, all the way times S minus Zn divided by B0, S minus P1, S minus P2, the rate of S minus P n. This is n, right? So in this case, this is the numerator. This is denominator. Okay, so just like I mentioned earlier, the roots of the numerator polynomial, this of k for instance, are called the zeros of S of S. Now, should any of these roots turn to 0, let's say z1, z sub 1 is 0, s minus, let's say when s is the same as z1, so z1 minus z1 will be 0, you realize that the numerator reduces to 0, then it means the Laplace transform reduces to 0. So technically, a 0 is a value that forces the Laplace transform to 0. And also, the roots of the denominator polynomial, let's say p sub k, are called the poles of the Laplace transform. And you observe that when s, for instance, is the same as p1, then this reduces to 0. Okay? And once this reduces to 0, whatsoever we have a numerator divided by 0, we tend to infinity. So in other words, the poles forces the Laplace transform to infinity. But a pole is a value that forces first the denominator itself to 0, forces the denominator of the Laplace transform to 0. And then a pole forces it forces the denominator to 0, and then consequently it forces the Laplace transform to infinity. Because anything divided by 0 is infinity. Just before we solve a few examples, I think it would be necessary to revise some of the verifiable Laplace transform pairs and some properties. Okay, so now considering the verifiable Laplace transform pairs, well, we already played with some of them because of our study, taking care of this. Sure, we just solved this and we saw that this was a right-sided signal. Right-sided signal. And you can see from the region of convergence, is greater than this value, and this is less than this value. So this is the left-sided version of it, left-sided signal. And should you plug this into the Laplace transform formula, and you arrive at this, and we arrived at this. And the same goes for this. So should it be, for instance, t when n is 1, tu t, so that would be 1 over s squared, right? So all the way. But the interesting part in all of this is that should we have something like this, probably you already solved. And solving, you saw that s of s is the same as 1 over s plus a. Then what do? Now, once you are able to identify the region of convergence, you can as well replace without necessarily using the inverse Laplace transform formula, and evoke this to say, well, s of t is the same as e minus at u of t. Okay, that's how to use your Laplace transform pairs to transform from the frequency domain to the time domain in the case of inverse Laplace transform. And we have quite a few interesting properties which we have been playing with. So we should be used to them now. The linearity property, time shifting, scaling, time reversal in the time domain, and the equivalent in the frequency domain. We made mention of this, that convolution in time is multiplication in frequency, and all the way. Good. So let us consider one example, which may make things even more interesting. So let us consider, okay, let's break this into 2 parts. Sufficient. Let's make it 3. Let's break this into 3. Okay. This will be sufficient. So now let's assume we have s of s given as 2s plus 4 divided by s squared plus 4s plus 3. Now, what do we want to figure out? So let's say we want to figure out stability, the region of convergence, and the inverse Laplace transform given these 3 conditions. And sigma is greater than -1. Now this is right-sided signal. Then I and sigma is less than -3. So you can tell by inspection that that is a left-sided signal. Then the third condition will be -3 less than sigma less than -1. So that should be a string. Okay. Now, good. Now that we have this kind of problem, so what do? In order to resolve this, we have to solve this partial fraction. So let's say by partial fraction decomposition. Now recall that we mentioned Well, it's usually not too interesting using the formula for the inverse Laplace transform to derive the time domain equivalent of the frequency domain representation, but we could use the Laplace transform pairs and do some partial fraction decomposition. So that's exactly what we want to do. So S of S will be same as 2s plus 4 divided by x squared plus 4s plus 3. So the same thing as 2s plus 4. So if we resolve this, that will be x plus 1 factors s plus 3. Partial fraction of this type, that will be over x plus 1 plus b over x plus 3. So if we multiply this entire aspect by this denominator, we should be able to arrive at a solution. So s of s equal to 2s is 4 divided by s plus 1 s plus 3 s plus 1 is b over s plus 3 multiplied through by s plus 1 s plus 3. So this will truncate this, so going to have 2x plus 4, and this will truncate this, so that will be a into bracket s plus 3 plus b, this will truncate this, b into bracket s plus 1. Okay, and then can further expand this, that will be as plus 3, a plus bs plus b, right? So collect like terms. So that will be the same as 2s plus 4 is the same as ab, a plus b, s plus 3a plus b, right? 3a plus b. Now, if we compare the left side and the right side, so this part corresponds to this part, while this part corresponds to this part. So, collect like terms such that for parameter s, so we have a plus b is the same as 2. For the constant k, which is 4, 3a plus b is equal to 4. So this is equation 1, this is equation 2. So we can solve these simultaneous equations, and then what do we get? A is the same as 1, and b is the same as 1. So hence, by partial fraction decomposition, 2s plus 4 divided by s plus 1, s plus 3 is the same as 1. AB is 1, 1, s plus 1 plus 1 over x plus 3. So using the Laplace transform pairs, we can evoke whatever one we evoke here. But is it right-sided? Is it left-sided? So the damping coefficient or the damping factor will help figure out if it is a right-sided signal or a left-sided signal based on the Laplace transform pair. Okay, let us therefore begin our investigation. Okay, So now we have the first part, which is I. And okay, and that is sigma is greater than minus 1. Okay, and if that's what it is, then the region of convergence for S of S is going to be the real value of S, which is greater than minus 1. So by intuition, we know we're going to have a graph that looks something like this. This is j omega, this is sigma, and this is minus 1. Since it's greater than minus 1, so values here will not exist. So it's going to look something like this. So it's the right side of sigma. Okay. So hence, S of t based on this condition is a right-sided sigma. Okay. So if that's what it is, we can take the Laplace transform. And for the right-sided sigma, 1 over s plus a is the same as epsilon minus at u of t, right? So based on this condition, our Laplace transform for this problem, S of t, based on this condition, having a right-sided sigma, and this is the right-sided version for the Laplace transform pair, then when a is the same as 1, so we are going to have this. Okay, so I'm going to have S of t to be the same as e. A is 1 and minus at, that's 1 times t is minus t, u of t plus epsilon minus 3 when a is 3, that's 3t, u of t. So technically, I can compress this minus t plus epsilon minus 3t to brackets t. That is the Laplace transform. For that. And now you see that we want to also test for stability. You see that j omega is within the region of convergence. So this system is stable. Okay. So finally, we can also mention that the system is stable since the region of convergence includes the j omega axis. Okay, so let us consider the second point. At sigma less than minus 3. Now, we know that the region of convergence of x of s is the real part of s, which is less than minus 3. And by inspection, we see that if we draw the x-plane, is j omega, is sigma, this is minus 3, right? I said it is less than. Now, parameters here are greater than minus 3. So if this is the line, so this part is less than minus 3. So this is the region of convergence. So we can tell that this system is not stable. Okay. So based on this deduction, we also know that the region of convergence is to the left. So this is a left-sided signal. Left-sided, right? This is on the region of convergence. Okay. This is arrows. So we can tell this is a left-sided signal. So recall that 1 over s plus a is the same as minus epsilon minus at u minus t. This is the inverse Laplace transform from the Laplace transform pair for the left-sided signal. So from our partial fraction, we'll have 1 over. So since s of s is 1 over s plus 1 plus 1 over s plus 3. Based on this condition, we have a left-sided signal. Recall, we had a right-sided signal here based on this condition, but this time we have a left-sided signal because of this condition. So, based on the Laplace transform pair, what we now have here is minus epsilon, where a is 1, minus t, u of minus t, plus minus epsilon minus this 3, right? 3 is 3. So that's a is 3 minus 3 t of minus t. So this will give us minus epsilon minus t u of minus t minus epsilon minus 3t u of minus t. Okay, so this is going to give us minus t epsilon minus 3t minus t. This is of t, of t. So the inverse Laplace transform is. And by inspection, you can see that the region of convergence does not include J omega. So here, the system is unstable since the region of convergence does not include the J omega. Okay, let us consider the third condition. Third condition. That's so we have minus 3 less than sigma less than minus 1. Okay, and based on this, we know that sigma in this case is greater than minus 3, and sigma is less than minus 1. That's what it is. So this is less, minus 3 less than sigma, so meaning sigma is greater than minus 3 and sigma less than minus 1, right? So now if we interpret this properly, we see that the region of convergence here, convergence of s of s, is minus 3 less than the real value of s less than minus 1. So by inspection, observe, should we draw the s-plane? This is j omega, this is sigma. Now we have minus 1, we have minus 3. Now, sigma is greater. Okay, let us draw the lines first. These are the vertical lines for -3, -1. Now, sigma is greater than -3. So this part is greater than -3, right? And it is less than -1, and this part is less than -1. So it forms a strip. Okay, so the region of convergence forms a strip, and it does not include the j omega, so it's not stable. Okay, fine. And you will see that at -3, this is -3, this is -1. At -3, it is right-sided, right? It's greater than -3. So at -3, we have right-sided signal. Now, at -1, it is less than, right? Region of convergence is less than 1. So it is left-sided. So at -1, the signal is left-sided. So this information is sufficient to derive our inverse Laplace transform, such that S of t is now a combination of, so left-sided at -1. So if it's left-sided, so we're going to be having minus epsilon minus t, u of minus t, right? Plus, at -3, it is right-sided. So it's going to be this version. E of -3t, u of t. That's the inverse Laplace transform. And then this system does not contain the region of convergence, does not include the j omega. So the system is unstable. That's about it. But so before we wrap up, you should note, I think I should just put this down. You should note that in the event that S of S strictly rational transform, it may be sufficient to evaluate the time domain representation by estimating the initial value, which is S of t equal to 0 positive, and the final value, which is S of t equal to infinity, using the initial value theorem and the final value theorem, respectively, without necessarily having to use the inverse Laplace transform method without necessarily having to deploy the inverse Laplace transform methodology. So what we're trying to say is, yeah, good. Well, we could adopt the inverse Laplace transform approach in terms of transforming from the frequency domain to the time domain. Okay, but in the event that we have a strictly rational transform, then we could deploy the final value and initial value theorem such that the initial value theorem is given by x of t equal to 0 positive, taking the limit for s of s when s tends to infinity, and in this case, the condition under which this theorem is valid is such that s of t is the same as 0 for t less than 0, and no impulse or higher order singularities at origin. Okay, and then the final value theorem, which is given as s when t t tends to infinity, this t when t is the same as infinity. Here we take the limit for s of s when s tends to 0. And then the condition under which this theorem is valid is such that s of s has no poles in the real values of s greater than 0. Okay, so but one pole at s equal to 0 may be sufficient. Okay, and then the region of convergence is right-sided. And well, we've got a number of standard tests where these theorems must have been validated with proofs and all of that. So I think this is a good place to stop. See you some other time. Bye.